This video is sponsored by Brilliant. In one of my previous Flat Earth videos, we looked up how humans figured out the distances between cities like thousands of years ago. And the answer was amazingly that people counted steps. This was a job you were trained to do, and it was incredibly accurate. I thought that was interesting. So I want to talk about more random things that we know/knew and how we know/knew them. So let's do it. Keeping on the same topic of Earth for right now, we knew the circumference of the Earth over 2,000 years ago. But it wasn't until about 250 years ago that we got an estimate for the mass of the Earth, before even knowing the gravitational constant g. And that happened in the Schiehallion experiment. In 1774, scientists hung a plumb line near the mountain Schiehallion in Scotland, and would use the deflection caused by the mountain's own gravitational force to calculate the mass of the Earth. This had actually been considered by Isaac Newton decades earlier, and he believed that the deflection would not be noticeable enough. But they ended up measuring a small deflection, like 1% of 1 degree. And with this, they were able to estimate the mass of the Earth. Now again, they didn't have big G, but they did have Newton's law of gravitation, and by doing a ratio of the force caused by the mountain and the force from Earth, that canceled G. And then the ratio is simply tangent of the deflection angle, which they were able to measure. They did still have to find the mass of the mountain though. How do you do that? Well, by finding the density and the volume of the mountain. Density can be estimated by just sampling rocks from the mountain and getting their density. That's easy. But the volume was found using surveying techniques to divide the mountain into prisms where they got the volume of each individually. Nowadays we would use 3D models, satellites, drone photos, and more. But that's how they did it back then. And if you're curious how they measured such a small angle, by the way, the main instrument was a zenith sector, or zenith telescope. This telescope is designed to measure very small angles from zenith, or from the vertical. Specifically, the angular distance stars are from the vertical. They actually set up 2 observation stations on each side of the mountain, both with their own telescope, and the tiny differences in the angle measurements of stars near the vertical allowed them to calculate the plumb line's deflection angle. Their calculation did yield a 20% error, so no, it wasn't the most accurate. But considering they didn't even have electricity, quite impressive for estimating the mass of a planet. But what's crazier to me is, how do we know what the center of the Earth is made of and its size? Because we've only ever dug 12 kilometers down. That's the most. We've dug 0.19% of the way to the center. So close. So how do we know what's at the center of Earth? The answer is earthquakes. When earthquakes happen, those waves travel across and through the entire planet. Small ones might not travel too far, but a strong earthquake can be detected just about everywhere on Earth. Now, earthquakes release 2 kinds of waves. P waves, which are longitudinal, like sound waves, and S waves, or shear waves, that are transverse. P waves can go through liquids and solids, but S waves cannot travel through liquids. That's one way we can find out the outer core is made of liquid. Because as we track how an earthquake moves through the Earth, we find there are certain zones where no direct P or S waves show up. This section right here, everything over 105 degrees away from the earthquake, is the S wave shadow zone. No S waves show up there consistently, which is just one factor telling us there's a liquid interior blocking the S but not the P waves from getting to this area. And we can look back at the expected path the earthquake would take to find what that boundary line is between the mantle and the outer core. Then there's also the P wave shadow zones from about 105 to 140 degrees from the epicenter, where P waves don't show up because they're being refracted. And because we understand how waves will refract through different mediums, We can use their path and shadow zone to know the materials the waves must be going through, which is consistent with a liquid outer core and a solid inner core. We've also found that P waves all of a sudden speed up at a certain point within the outer core, which would happen at a medium change when going from liquid to solid, telling us more that, hey, there is a solid inner core here. These aren't the only methods that are used, but they are very strong evidence of our planet's makeup. Now, moving away from Earth topics, how do we know how many homeless people are in America? Yes, pretty random, but it has an interesting answer. There are multiple methods that can be used, but my favorite answer to this is we count them. Literally. It happens once a year in January, in one night. Volunteers and communities go out and count the homeless population, sheltered and unsheltered. It's done by the Department of Housing and Urban Development, and it's called a point-in-time count that's been happening every year for the last 20 years. And I found that interesting because there are better methods for counting, which explains how we can know things like how many fish are in Lake Michigan, or how many bears are in a certain forest. We can do it with this formula and the mark and recapture method. It's very basic, but you sample, let's say, 100 fish from a lake. Then you tag each one of those and then let them go. You give them enough time to mix back in with the environment, and then you take another completely random sample of 100 fish, and however many of the previously tagged fish are in this new sample gives us an estimate for how many of these fish are in the entire lake. You just take the original sample size, multiply it by the second sample size, which was the same in our case, and then divide by the number of recaptured animals that were originally marked. That's our estimate. So if you captured 100 fish each time you sampled, and the number of tagged fish that reappeared in the second sample is 1, then the estimate would tell us there's 10,000 fish in this lake. Had we seen 5 repeats, then the estimate would be 2,000 fish total. And at 50 repeats, there'd be an estimated 200 fish. It's really just a simple proportion, and it only requires sampling twice. So yes, we count, but we do it strategically, and that's one way we know animal population sizes around the globe. Similar math was actually done during World War II, when the Allies tried to estimate how many German tanks were being produced each month. They did this with some basic math and the serial numbers they found on tanks left in battle, because these serial numbers increased numerically, so they could get estimates for how many were being produced. This problem is actually called the German tank problem, and in simple terms, you imagine you have a bunch of pieces of paper labeled 1, 2, 3, all the way up to N, and no, you don't know N, you don't know the total number of pieces of paper. And then those papers are shuffled and you select a few at random. Then the question is, given these numbers that you randomly pulled, what is likely the biggest number in the pile, or what is N? That's the German tank problem, and here's one of the formulas to make the estimate. And again, surprisingly, very simple. N is the total number of cards or tanks predicted that we're trying to find. M is the highest number that you pulled or sampled, so in this case 546. And K is how many cards or tanks you pulled or sampled. In our case, 5. So this tells us that N is probably just about 654. Now, had we sampled 100 times and still our maximum was 546, then the equation predicts that the biggest number in the pile is 550. And intuitively, that makes sense. Because imagine if 1,000 was the biggest number, that was N. Well, out of 100 trials, if you never pulled anything more than 546, well, that's just insanely unlikely. So yes, this equation comes from how close the biggest sampled number is expected to be to the maximum number N, based on how many cards you pulled. And again, this was incredibly accurate during World War II. So there you go, lots of unique ways just to count things. And if you want to dive more into cool applications of math like you saw here, then I highly recommend checking out Brilliant, the sponsor of this video. Brilliant is a learning app that helps you become a better thinker and problem solver with thousands of visual interactive lessons in math, science, programming, data analysis, and AI. Each lesson on Brilliant is filled with hands-on problem solving that lets you play with concepts, which is a method proven to be more effective than just watching lecture videos. They help you build an understanding from the ground up through interactive exercises, engaging practice problems, and even daily encouragement that keeps you motivated. I personally enjoy the real-world applications the most that they focus on in so many of their lessons because I learn how both advanced and basic concepts can apply to complex problems, giving me a new understanding of why we learn what we do. So help build your critical thinking skills not through memorization, but by building real knowledge through their first principles approach by clicking the link below or going to brilliant.org/ZachStar where you can start for free. And their premium subscription comes with unlimited daily access to everything on their platform. You can also scan the QR code on the screen now. And with that, gonna end that video there. Thanks as always to my supporters on Patreon. Social media links to follow me are down below, and I'll see you all in the next video.